It's Mrs. Mafucci, and I want to continue our study of thermodynamics by looking at enthalpy of reaction or heat of reaction, delta H. Remember, delta H, or heat of reaction, is the energy that is transferred during a chemical or physical change. It is the energy gained or lost by the reactants when they change into products. There are 5 different ways to determine the heat of reaction, or the delta H. Number 1 is by using the heat found in the balanced equation. Number 2, by using experimentation and the formula delta H equals mCp delta T. Number 3, using the standard heats of formation found in your reference tables and the formula delta H is equal to the sum of the heats of formation of products minus the sum of the heats of formation of reactants. Number 4, using Hess's law. And lastly, number 5, using potential energy diagrams. Now, some of these methods I know you are aware of, but there are others that you don't know how to do yet. So let's consider these 5 methods individually. Number 1, using the heat found in the balanced equation. The first thing that you should notice in this equation is that heat is on the left side of the arrow. Heat is on the same side as the reactants. That means the reactants combine along with the 182.6 kilojoules of heat to produce the 2 moles of NO. Heat is required for this reaction. This is an endothermic reaction. The reactants must absorb energy to be converted into products. Since this is an endothermic reaction, delta H is positive 182.6 kilojoules. Let's consider a different equation. In this equation, the heat is on the right side of the arrow. It's on the same side as the products. In other words, energy is a product of this reaction. When nitrogen and hydrogen combine to form ammonia, 91.8 kilojoules of heat are produced along with the ammonia. This is an exothermic reaction. The nitrogen and hydrogen must lose energy to be converted into ammonia. Since this is an exothermic reaction, we know that delta H is negative. The heat of reaction, or enthalpy of reaction, for this equation is negative 91.8 kilojoules. Let's look at the second method. We can determine the enthalpy of reaction or heat of reaction by performing an experiment. By measuring the change in temperature of the surroundings. And we know that the heat gained by the surroundings equals the heat lost by the system. Likewise, the heat lost by the surroundings equals the heat gained by the system. In other words, if the temperature of the surroundings goes up, that means delta T is positive. That means the surroundings experience an endothermic reaction. This means that the system has experienced an exothermic reaction. The system has lost energy to the surroundings. The heat gained must be equal to the heat lost. So when you calculate delta H, all you have to do is change the sign. The third method for determining the enthalpy of reaction or heat of reaction is from using your thermodynamic data found in your reference tables involving heat of formation. The heat of reaction is equal to the sum of the heats of formation of products minus the sum of the heats of formation of reactants. Remember, it's always products minus reactants. Heat of formation is the amount of heat gained or lost when 1 mole of a compound is formed from its free elements. If you look at those three equations at the bottom, you'll notice that they are all equations that produce 1 mole of product. These are all heats of formation equations. 1 mole of product is formed from free elements. Remember, the heat of formation of a free element is 0, so you will never find a free element in your heats of formation tables. The next method involves using Hess's law. Hess's law states that if a reaction is carried out in a series of steps, the delta H for the reaction is the sum of the individual delta H's for each of the steps. So if you look at the diagram on the right, if reaction 1 plus reaction 2 plus reaction 3 combine to give you an overall reaction, that means that the heat of the overall reaction is equal to the individual heats of reaction for reaction 1, 2, and 3. All you have to do is add them together. Let me give you a simple example. Given the following, consider that the first reaction is this: nitrogen plus hydrogen forming ammonia with a delta H of negative 92 kilojoules. Now suppose this reaction then combines with reaction 2, which is this reaction right here. Notice that the delta H for this reaction is positive. When ammonia and water combine to produce nitrogen dioxide and hydrogen gas, it requires 1128 kilojoules of heat. Well, let's now combine these two equations with the last equation, reaction number 3. Reaction number 3 is when 4 moles of hydrogen react with 2 moles of oxygen to produce 4 moles of ammonia. The third reaction is when 4 moles of hydrogen react with 2 moles of oxygen to produce 4 moles of water. This reaction has a delta H of negative 968 kilojoules. Now let's see what the overall reaction is when we combine all of the reactants on the left side of the arrow and all of the products on the right side of the arrow. When we do this, we want to combine like terms. We come up with an overall reaction of this: nitrogen plus 2 ammonias plus 7 hydrogen plus 4 water plus 2 oxygen produce 2 ammonias, 2 nitrogen dioxides, 7 hydrogens, and 4 waters. Now, just like in mathematics, when you see the same thing on both sides of an equation, you can cancel those substances out. Do you see how there are 2 moles of ammonia on the left side and the right side of the arrow? They cancel each other out. Notice also that there are 7 moles of hydrogen on the left and 7 moles of hydrogen on the right. They also cancel out. Notice water also cancels out. When we now combine the substances that have not been canceled out, we come up with an overall reaction of nitrogen plus 2 oxygens yields 2 nitrogen dioxides. And how do we find the delta H? All we have to do is add up the individual heats of reaction. This equation has a delta H of positive 68 kilojoules. Hess's law tells us that it doesn't matter how you get from reactants to products, whether it's in a single step, like path A, or in a series of steps, like in path B, delta H is the same. Products minus reactants. Well, let's now consider the last method for determining delta H. We can use potential energy diagrams and use the formula that delta H is equal to the potential energy of products minus the potential energy of reactants. Let's look at 2 examples. This is an endothermic potential energy diagram and represents the chemical reaction shown above. When carbon, hydrogen, and oxygen combine to form glucose. Look at the potential energy diagram. Do you see the interval that represents delta H? Energy is on the left side of the equation. This reaction is endothermic, and delta H is positive. The reactants must gain energy from the surroundings to change into products. Carbon, hydrogen, and oxygen must absorb energy from the sun to be converted into glucose. Let's consider this exothermic potential energy diagram. In this diagram, notice that the products are at a lower energy than the reactants. That means the reactants must lose energy to change into the products. Energy is on the right side of the equation. The reaction is exothermic and delta H is negative. The reactants must lose energy to the surroundings to change into products. Hydrogen gas and oxygen gas must lose energy to be converted into water. This is a potential energy diagram of an endothermic reaction. You may want to pause this video right now, copy down this diagram, and make sure you label what each of the lines represent. This is the potential energy diagram for an exothermic reaction. It would be important for you to label each of the lines and know what each represents.